चालू करेंगे. Come on, action.
In this video, we will discuss about the design of two-way slabs. In the previous class, we have discussed about one-way slab. This class we will discuss about two-way slab, or it is also called slab spanning in two directions. Slab spanning in two directions. So what is this slab spanning in two directions? We have discussed that in a slab we got two dimensions. One is shorter span, one is longer span. If ratio of longer span to the shorter span is greater than 2, then the slab is categorized as a slab spanning in one direction, or it is also called as one-way slab. If ratio of longer span to the ratio of shorter span is less than or equals to 2, then this slab is categorized as slab spanning in two directions or two-way slab. In two-way slab, the design will depend on edge conditions, as I said. Edge conditions, whether all edges are supported or not. What is this edge condition is all about? If you take a look of a slab panel, which I have shown here, right? Now, in a slab, we got 4 corners. If all these 4 corners are supported, if all these corners are supported, or if all these edges, this is one of the edge, this is second, this is third and fourth, all these edges are supported or not supported. If it is supported, the design will be something different. If it is not supported, the design will be something different. Now, in annexure, it is clearly mentioned how to design a slab which is spanning in two directions. Right? So, if I say the slab is supported on one edge conditions, and support conditions. The two-way slab design criteria is based on design criteria is based upon edge conditions and support conditions. Now, if I take a look of this slab, this edge is supported. So, this edge is supported, that all edges are free. And however, the edges, some of the slab panels are continuous, some of the slab panels are not continuous. Like for example, if I talk about a hall in your house, a hall is supported a continuous to the bedroom, kitchen, but not continuous to the veranda. Any internal slab is continuous to all sides. Slab is continuous to all sides, then there is an internal panel continuous slab. If either of the slab is not continuous, then its conditions will differ. Now, you have different conditions to this. Now all sides are supported and all sides are continuous. This is an interior panel. We categorize this as interior panel. Interior panel is what? All sides are supported and all sides are continuous. Now, how different are these slabs when compared to one-way slabs? The only difference is in one-way slab we calculate bending moment using the theoretical conditions that is WL squared by 8. Whereas these slabs analysis is different because the analysis has to be done using inline theory. The dotted line shows the crack pattern of the slab. So as I said, we need to have a separate theoretical principles of hypothesis where we could draw conclusions to calculate the bending moments, shear force, thereby could provide steel reinforcement to it. So one of this method which is recommended is in stipulated IS method, which is also given in annexure. You can take a look, right? Now, what is this annexure says is, when slab is spanning in two directions, you need to calculate two bending moments, that is mx and my. Slab spanning in two directions, you need to calculate two bending moments, mx and my. And this is the equation, and this value should be multiplied with the corresponding coefficient, that is alpha x, and this is alpha y, and this is WLY square. This is given in I square 2. This is how the alpha x and alpha y shall be calculated when continuous panel is there. When edge conditions are changing, where one edge is not continuous or two edges is not continuous, two opposite edges is not continuous, two corner edges are not continuous. When these conditions changes, then these alpha x and alpha y coefficient values subsequently should be changed, and these values are also given in IS good table of form in arrangement. Now, in this design, we will talk about much why this has got different principles, and when you compare with the one-way slab is, the entire behavior of the slab will totally different when you compare the same one-way slab with a two-way slab. Your two-way slab looks something like this. I am talking about longer span by shorter span ratio is more than 2. Right? Now, this slab either bends like this or either something like this. Now, but this slab will behave as a cup fracture where these corners are lifted up. Right? Corners are lifted up due to torsion. A torsion is developed due to the bending of the slab, and due to that torsion, the corners of the slab are lifted up. So, which makes the slab corners cracking more. You know, imagine a slab totally falling down, something like that. Slab will be, in a good position, but slab comes off because of the cracking in the corners. If this is happening, then the slab has failed due to lack of provision of torsional reinforcement at the corners. The slab has excessively bent and the cracks are developed at the corners and it totally fell off. So this can be avoided by providing additional torsional reinforcement in the corners, which is also given in the corner. Also, it is said that your entire slab shall be divided into middle strip and edge strip. This is for longer span, and this is also applied for the shorter span, even for the shorter span also. For example, if I take the same slab, it is two-way only. It may be looking like one way, but it is two-way. Let us assume that. Now, this is middle strip. This is edge strip. Okay. Now, the dimensions of these middle edge strips is given as, you can assume this middle strip as 3/4 of Ly, and this is the rest balance is 1/4 by 2 is L by 8, by 8, and this is also Ly by 8, and similarly this is 3/4 of Lx, because this is shorter direction span, and this is how much balance? This is 1 Lx by 8. This is Lx by 8. Okay. Now you have to provide main reinforcement here. Right? And distribution reinforcement here. Similarly, you have to provide main reinforcement here and distribution reinforcement here. In edge strips, you have to provide distribution reinforcement, and in middle strip, you have to provide the main reinforcement. Main reinforcement should be calculated using these equations which is given in the image. And R5s and R5 are the bending moment coefficients. Which depend upon Ly by Lx ratio. Right? It is often also called in some of the textbooks as R. Okay? So we shall do one problem. Please copy, note down this problem. I will dictate it. Design a RCC slab for a room measuring 5 by 6 size. Room size is 5 by 6. The slab is simply supported on all 4 edges. 4 edges are simply supported where corners are held down. If you are saying that corners are held down, then you need to calculate the torsional reinforcement. If corners are not held down, then you need not calculate the torsional reinforcement. If corners are held down, if you are pulling corners out for not getting lifted up, the only way you could not allow the slab to held down is to provide this torsional reinforcement. You need to calculate torsional reinforcement for this problem. So the slab is simply supported on 4 corners, 4 edges with corners held down, carries a superimposed load of 3 1000 Newton per meter square. $3,000 per meter square, inclusive of floor finishes, so this includes floor finishes also. And he said use M20 grade concrete and Fe415 steel. So he also mentioned use IS4 method. So how do we do this is first we need to calculate the bending moments and thereby we distribute it per the reinforcement. Okay. So first step is to write down the design constants. Design constants. The design constants for this problem are FCA is 20 Newton per mm square and Fy is 415 Newton per mm square. Right? And as because Fy is 415, you can calculate X max by the limiting neural axis ratio, that is 0.48. So these are the design constant. And second step is now you need to calculate the bending moment. So calculation of bending moments and shear force. Now in calculation of bending moment shear force, we got to have first we need to calculate the loading, calculation of loads. In order to calculate the loads, you need to assume the depth of slab. As I said, depth of slab from serviceability criteria or reflection criteria. It is simply supported beam from reflection criteria. Span by depth for given as simply supported beam. From code, it is given as 20. Now we got two spans here, longest span we got and shortest span we got. Now it is always said in order to take shortest span. Now I am taking shortest span 5000 divided by 20. Now in IS code, we need to calculate a modification factor because this is slab. We need to calculate the modification factor which depends upon the percentage of steel which is provided. As because percentage of steel we doesn't know, not yet calculated, so we assume PT% as 0.2 percentage for under reinforced section. And from IS code book, from IS 456, modification factor for this modification factor. There are certain curves, and for the certain curves, you can calculate the modification factor from IS 456. It is approximately 1.68 you will get. Now you need to multiply this 1.68. So span is 5000 divided by depth, that is equal to 20 into 1.68. Now from here you can say the depth small d equals to 148.8 mm. So overall depth is given by capital D plus cover plus diameter by 2. Right. Now this is small d. Here it is given as 148.5. So let us take that only 148.58 plus cover. Normally it is taken as 15 to 21. I am taking 20 as because this is two-way reinforced slab 20, and I am assuming 8 mm diameter, so 8 by 2. So I will get an overall of 172.8 mm. So hence say this as 180 mm and small d as 150 mm. See, small d and 150. For our calculation purpose only, we have to take this. Then when you have got overall depth and d, all that we need to do is calculate the measurement, check whether the 150 mm is good enough to take this thing or not. So before doing that, we need to calculate the loads. So first load which is given to you is you need to calculate the weight of slab. Weight of slab, that is set weight. We also call this as set weight. How will you calculate? Thickness is 1 pint. Overall thickness is how much? It is 1/8. 1 meter width you have to take, 1 meter depth you have to take, 25 is the density, kilonewton per cubic meter. You get this value as 4 per meter. You are taking per meter square, right? So per meter you can write. Then what else we got? We got line loading or superimposed load. Superimposed load is directly given as 3, so we multiply 1 by 1 and 3 kilometer per square meter. So this will become 3 kilometer per meter length. And sum them up, there is no other load, this includes everything. So 7.0 kilometer per meter is total weight. Now this is the working load. So ultimate load is given by factor of set is 1.5. Like into 7.5 is 11.25 kilonewton per meter. Right? You need to calculate the effective spans. In the calculation of effective span, now you got clear span there, you got center to center span. Right? Now effective span as per IS code is the least of 1 clear span center to center span or clear span plus effective depth. So I'm talking about this Lx and Ly. This should be the effective span should be considered. So center to center span, we already need to calculate the both of them. So we will calculate Lx and Ly also for our calculation purposes. So Lx is 5 and we did not got the support widths, right? So we shall assume support widths as 0.3. So we got 0.3 into 2 into 2 and 5.3 could be the center to center span along shorter direction, and 5 plus effective depth we have taken as 0.15. This will give you as 5.15 meters. These both I have calculated in shorter span. Similarly, you can calculate for longer span. It is how much? 6.3 meters and 6.15 meters. So least in longer span is 6.15 and least in shorter span is 5.15. So note down this value there. These are the effective spans where we need to substitute wherever the spans will come. So, right, and in order to calculate moments, you need to calculate alpha x and alpha y, which depend upon Ly by Lx ratio, that is R. So we need to calculate Ly by Lx. Now this Ly by Lx is no more 5 you have to take. Now you have to take the effective span only. Effective span is given by Lx is 6.15, longer direction. This is 5.15. Shorter direction, and this ratio will give you 1.2 value. And from IS scoreboard, alpha x can be calculated as 0.072 and alpha y can be calculated as 0.056. Okay. So now you can calculate bending moment as in longer direction. We calculate first longer direction. That is y is given by alpha y WLx square. For both of them in code book, Lx square is only given, not Ly. Okay. Alpha y we have evaluated as 0.056 and this is 11.25 and this is 5.15 and we get this as 16.71 kilonewton meter. Next My. This is ultimate moment again. Similarly, in shorter direction, mu x is given by alpha x into WLy square. That is, alpha x is given as 0.072 into W is 11.25 into again this is Lx. Lx is 5.15. You will get this value as 21.48 kilonewton meter. So you have got mu x value, you got mu y value. Now you need to calculate the edge strips and middle strips as I said here, right? Calculation of and middle strip. Now you've got shorter direction, you've got longer direction. So first we will calculate for shorter direction. Shorter direction, middle strip, middle strip is given by 3 by 4th of short direction means Lx. 3/4 of Lx, and edge strip is given by 1/8 of Lx. So 3 by 4th of Lx is given by 3.87. So sorry, for shorter direction you have to take Ly, for longer direction you have to take Lx, right? And then you y. This value is given by 3.87 meters, and this value is given by 0.64 meters. Now, I said that in short direction you have to take middle strip, taking the span of longer direction, and in longer direction. Now, after calculating the middle strips and end strips, you need to remember that you have to take the longer span in order to calculate the middle strip and end strip along short direction. You have to take shorter span when you are calculating middle and end strip in longer direction. This is stipulated in IS code, right? Next is when you have got edge strips and middle strips. Now let us check whether the given thickness of slab is able to resist the bending moment which is given. From these both, the highest being 24, 21.48, we'll take that moment and we'll check. Okay, so check for effective there. Now assuming it is a balancing section, now I'll equate the ultimate moment along which direction I got? X direction to the moment of resistance of balancing section, right? That is how much it is? 0.36 FCK XU max by D into 1 minus 0.42 XU max by D into V D square. Okay. Now, by substituting the values of desired constant in this equation, that is 0.36, FCK is 20, XU max by D is 0.48 into 1 minus 0.42 into 0.48 into B is 1000, slab is designed as 1 meter width. This is D square, and movement which is coming is 21.48 into 10 power 6, because all these values are Newton value. So this should be Newton value. The required at got as 88.2 ml, but D provided is how much is D provided? I have provided 150 ml. So provided is more than actual required. So hence, say. Now once you ensure that the provided depth is good enough, then you need to calculate the steel reinforcement. Now steel reinforcement is not that much difficult, although you need to take the required bending moments at required spans. For example, likewise you calculated here the calculation of tension for shorter and longer tension. In the similar way, calculation of steel is also be done for shorter and longer tension. Calculation of steel reinforcement. Now first we will go for shorter span, right? By assuming this section as under reinforced section, we will do it, right? Under reinforced section. Now for under reinforced section, I have mentioned that for shorter span, you have to take shorter span movement. Okay. And you have to equate the moment of resistance of under reinforced section, that is 0.87 F5 AST into D minus 0.42 XU. Again, XU we already know as 0.87 F5 AST divided by 0.36 FCK BT. Now AST is not known. You calculate XU in terms of AST. Now you back substitute this XU here. Again, AST is not known. Now this entire equation is equated to movement which is coming, that is 21.48 into 10 power 6. Now a quadratic equation will come. From quadratic equation, AST can be calculated as 403.2 mm square. Now spacing can be calculated as, I am assuming dia of bars as 8 mm. Now I said spacing is given by 5 by 4. The numerator you have to take cross section area divided by required area 403.2 multiplied by 1000. You will get spacing as 124.7 mm. Now let us say this as 120 mm. Right? Now write a statement. Provide 8 mm dia at the rate 120 mm center to center in middle strip of 4.61 meters width, right? In mid portion, how much? 4.61 meters. You have to provide 8 mm of 120 mm center. How about this edge strip? Now, edge strip you have to provide minimum reinforcement. So, along edge strip you have to provide minimum reinforcement. Now, as because you are taking Fe415 grade steel, minimum reinforcement is given by 0.12 percentage of gross area. So this is 0.12 divided by 100 into breadth into overall depth. So this is 0.12 times 1000. The breadth is 1000 into overall depth is how much? I calculate as 180. Now if you are supposed to calculate this value, you will get this as 216 mm square. Now write down the statement of we need to calculate the spacing. Now how much dia you have to take is depends. 8 mm I am taking. Here 400 I am taking 8. 216 also 8. What will happen is, as because this is 2 times, this is 400 I have got to 140. This is 216 I will get 240. Simple. 5 by 4 into 8 square divided by 216 into 1000. Say approximately this as 240. Write down the statement here. Provide 8 mm dia at the rate 240 mm center to center in edge strip of 0.77 meters wide. For the similar calculation has to be done for long span, right? In long span, the changes will happen in MUY equals to MR equals to 0 by rest all will be same change, will not change. So MUY will be how much? 16.71. Here value is 16.71. When this becomes 16.71, now 5 kilonewton meter is less, so this will come around 300. So this will come around 150 maybe. So you can provide 8 mm at 150 mm in middle strip of 3.87 in longer direction, right? So here 8 at the rate 120. Here 8 at the rate 240. Maybe I am guessing you get 8 at the rate 150. And here 8 at the rate 300. Right? So in the next step, when the second step is third step, second step is what? You need to calculate for longer span, like how I did for shorter span. You have to do, right? This is how you do. I'm guessing that this could be the values. Right? In the next step, we have to calculate the torsional reinforcement. Right? Torsional reinforcement is provided at the corners in the sense. Now you have calculated the steel in the middle strip, in the edge strip, right, in short direction, and in a similar way, You have calculated the steel in longer direction, that is middle strip and edge strips. You also need to calculate the corner reinforcement because corners are held down for lifting, so you have to provide this mesh at 4 corners, right? So we will calculate this in annexure G. If you take a closer look, annexure that is slab spanning in 2 directions, it is clearly said that when slab is held down or slab is not allowed to lift up, you have to provide a torsional reinforcement of certain amount, and that clauses are given. Please read it out by yourself. Now I shall do the calculations part from my side. Okay. Now next step is calculation of torsional reinforcement. So all that it is, how much is this width you have to provide, and how much is the area of steel, how many steel bars of how much this thing you have to provide, right? So this is done. First is you need to finalize the size of torsional mesh, right? It is given as shorter span, 1/5 of shorter span in the given clause. So effective shorter span is 5.15. So 5.150 divided by 5 will give you a value of 1030 meters. And the area of this reinforcement is you have to calculate 3/4 of AST, which is calculated in shorter direction. Right? So that is 3/4 of area of steel calculated in shorter direction is how much? 403.2. So if you calculate this value, you will get as 302.4 mm. And you got this area, you can calculate spacing by assuming some diameter. Let us take 8 mm is my diameter. So 5 by 4 into 8 square divided by 302.4. This will give you a value of 166 mm. So you can say approximately 150 mm center to center. So how many bars? Provide, but you always have to write a statement when you complete the reinforcement design. Provide 8 mm bars at the rate 150 mm center to center as torsional reinforcement for a width of how much? 1030 mm from corners on both faces or both sides of slab. That is top and bottom. That is, if you have slab, I got slab here and I got this thickness as 180. Now you provide steel here. This length is 1030. Also got steel and we also got bottom shape. Now this is given by 8 and divided from 15 which is other than the main shape. You also get main shape, right? So the detailing part of mainstream we will discuss in next video. So for the time being, remember this: how much is the middle strip values, how much is the edge strip, and also you need to remember this value which is provided as torsional reinforcement and some of the conditions which are stated, because if you are providing middle strip, the middle strip reinforcement should go into the edge strip should come into the middle strip. If it is a continuous, there are certain value strips. We will discuss all those things from stipulators which are provided in the XLG for the slab in next class.